Hi, good evening, everyone. My name is Rajat, and today I'll be presenting you guys on a topic called fraud networks. Let me share my slides for that. Yeah, before going through the presentation, I'm an engineering manager. I work for Booking.com. I'm based out of Amsterdam. So it's currently 11 o'clock here. So apologies if I may sound a bit sleepy. But yeah, I'll try my best to wrap it up in the next 25 minutes or so. Please feel free to drop any questions that you have in the chat that is available in this session, and I'll be very happy to answer all the questions towards the end. So today's agenda is going to look something like this. I'm going to walk through a problem statement that we solved using graphs, briefly discuss the technology that we used for that, both in terms of engineering and machine learning, and some of the next steps and challenges that we aim to solve with it in the future. Cool. Let's start with the problem statement. So Booking.com, as many of you might already know, we deal with hotel reservations. We also deal with flights and taxi reservations as well now. But this problem that we are trying to solve here is regarding fraud that happens in the world of payments. So I'll be walking through an example. Let's say a person tries to make a booking on our platform using a particular email on a particular device and using a credit card, right? Very simple scenario, happens in e-commerce industry very often, right? But what happens is it turns out that the person used a stolen credit card, and hence the merchant provided a chargeback for that transaction. That means someone claimed that my credit card was stolen and asked for a refund of the money that was charged from it, right? In this case, Booking being the agency here has to return the money that was charged from the credit card. Now, what happens if a different reservation happens that reuses the same credit card that was used in a previous transaction, but on a different device ID, right? Uh, would we want to block that or not, given we have a previous information that the previous transaction was used in a fraudulent scenario, right? Or let's say a different transaction happens using a different email, E3, let's say that reuses the second device, D2, but with a different credit card, right? So further away from fraud, but still quite connected with it, right? So what you might be seeing here is that a typical graph can be used to model this scenario, where the nodes or the vertices could represent the different identities that we have in the world of payments, and the edges or links are how often they are used together or in which scenario they are used together. Right? And yes, that's exactly how we modeled our use case, where emails, devices, and credit cards became the nodes that we have in the graph, and also the fraud nodes, of course, chargebacks, and the links became on when they were used together in a particular transaction. Right? It's a very interesting problem. It has some good characteristics that we use property graphs for modeling this scenario, where both the nodes and the edges need to store some information about what the email address was or what the credit card information was, right? And have some predefined schema. So only certain types of nodes can exist and certain type of edges can exist in the graph, not anything random. And there are certain challenges associated with this as well, because the networks can get very skewed. We will touch upon this a little bit later in the presentation. But if you might understand, there are few people who could use different credit cards and different devices like your laptop, your phone, and have very small networks. But the fraudsters, if they want to do like a scripted attack, brute force one using different multiple email addresses and thousands of credit cards, then the networks can grow a bit larger in the size as well. Right? And we have tight SLOs in our service requirement because the entire payment checkout funnel depends on this. So this makes it a bit of an interesting problem to solve, both using graphs, but on the engineering front as well. So I'm going to walk through some technology that we use to solve this problem. Graph databases become very handy in this respect. I think most of you would be already aware about it, but a graph database is a typical NoSQL type of database, but it is optimized for storing as well as querying graph-based structures, right? And the stuff that we use in our case is something called GenesGraph. It's an open source graph database, and it's optimized to store as well as query billions of vertices and edges in real time. It has a lot of support for providing concurrency because if you can imagine, maybe hundreds of users might be checking out of a booking.com funnel at any point of time. So you could have concurrent requests coming into your graph databases at any time, right? And on top of that, it provides it multiple functionalities out of the box, like caching of data in any layer, indexing of data as well, so that you can have fast retrieval, and expiration of data as well, so that if you want, you can keep your graphs up to a certain period of time and expire anything that's older than that, right? Apart from GenesGraph, we also use the Apache Tinkerpop framework. It's a API framework that's available for graph traversal and manipulation. It's simply for querying the graph using the Gremlin query language. I think it's a very common standard Gremlin query language that is supported in multiple languages and has a very clear API for querying graphs as well. So that's the entire stack in terms of graph that we use for modeling our problem. So how it works is underlying we have a NoSQL database. I think in our case it's Cassandra, and we use GenesGraph library on top of it to interact with the actual graph. I'll touch down a bit on the engineering bit on how we do the graph traversals and basically what information we find from it. The algorithm that we use is breadth first search. Again, a very commonly known one in the field of graphs. The good thing about this algorithm is it's linearly scalable with the size of the graph, and it handles cyclic loops very effectively. So you can start from any one particular node, and you can traverse everything that's associated with it. How we use this traversal is something I'll touch upon in after a few slides. But the idea is you start from something and then you explore a portion of the graph that's connected with it. Right? Now, as I mentioned before, the SLOs are a bit tight in our case, and we need to explore and compute these graphs in a real-time fashion, and sometimes within seconds as well, right? So there are certain optimizations that we need to keep in mind while we're exploring these graphs, right? One good thing is we that GenesGraph provides out of the box is it provides batching of queries. What I mean by that is you can keep all the nodes at a particular level, and in one single query, you can get all the nodes at the next level. So now that reduces the time for exploring the entire graph from its entire size, that's order of n, to order of log n, which is the depth of the graph itself. So let's say if a graph consists of n nodes but has height of only h, you only need to do h queries instead of n queries to find all the nodes in the graph. So that's an important one because that scales very well for very large and dense graphs, and which is an important bit which a lot of companies actually struggle with when querying graph databases. So it becomes very handy. Another optimization that we had and that was done by our own is usually when we are trying to infer from graphs, we insert data first into the graph and then query the subgraph from it. And that's the typical flow that ensures the data is consistent and we are getting the most up to date information. But that introduces some extra latency because we are spending a lot of time in insertions and then we are doing the query part. Now, what we actually do is we actually write asynchronously so that all the writes happen offline in a background job. And the reads that we do, we assume that the nodes that we wanted to write are already written, and we do like different traversals from all these different nodes and virtually merge the graphs together. So that separates the read path from the write path, and we are able to speed up the whole process of computing the graphs as well. So that's an important one as well, and worked very well for our use case. Now, I have been talking about we explore the graph, but then, okay, we have explored the graph. What is something we want from them, right? And that's the data science bit and forms the heart of the whole fraud detection mechanism for booking.com, right? And that's the graph features. These are the set of features that we obtain from the graph structures of our indicators, and we feed these features into our machine learning models, and the models learn based on top of them. Some of the features that we use and that have proved to be very useful in detection of fraud is one type of them is shortest path features. Shortest path algorithms are very well known in world of graph, and the idea is if you have a particular transaction coming in, how far is it from something that could be fraud? As you would have seen in the previous example, it could be like 2 hops away, 5 hops away, 7 hops away. So the closer it is to a fraud event, the more likelihood it is that something in the future is going to be fraud as well. We also have some other type of features based on the topology of the graph, like count features, like what is the size of the cluster, what's the size of a particular type of node in the graph. That gives you some value of what's the ratio of credit cards versus emails, or what's the ratio of uh, fraud labels versus the entire graph, and gives you an idea of what the graph consists of. Same for degree features. Degree is a well-known concept in graphs as well. That's the number of connections that a particular node has, and that also gives you some idea of the topology of the graph. And then what's the min, max, average degree of a particular type of node. Another interesting feature, and actually a very, very important one for us, is the growth features, is how fast the network is growing over the period of time. If you can imagine, a normal person would make bookings, once every week or 2 weeks or once every month. And for them, their cluster or subgraph can grow, very thinly over a period of time. However, in a fraud attack, it can grow very fast within minutes or hours, right? So these growth features are based on how much a subgraph has grown over the period of time, and that gives you some velocity features on what the fraud trend is looking like. And finally, we also have age features, which gives you the temporal bias of a particular graph on how old the nodes are in a particular graph, and gives you an idea of how relevant the information might be if you're computing a particular type of feature with these age worth of nodes. So yeah, these are the set of features that we use. And when we feed them into our ML models, they actually outperform a lot of traditional or conventional features that our models were using. And graph features actually really help a lot in detection of fraud. Some of the features that we haven't implemented yet, but are definitely on our mind, is page rank. It's an interesting one because it helps you understand the importance of a node in its local neighborhood, and can give you some extra information about how important a particular node is compared to others. And we can use this as weights for particular nodes in coming up with the final score of fraud. Another thing is also community detection. So right now, when we start traversing from graphs, sometimes the subgraphs can be thousands of nodes, and computing all the above features that we just discussed on 10,000 or 20,000 worth of nodes is not always feasible. So right now we rely on some static cutoffs on the depth of the graph and the maximum number of nodes that we explore, just to limit the size of the graph we want to explore. But community detection algorithms are also very important to help us find out the right portion of graph that might be interesting for our use case, so that we don't have to rely on these static cutoffs in the future. Right now, we also don't have weighted edges, but weights on edges might be an interesting scenario as well, where we can see a particular indicator is of high relevance or or low relevance for us, and we don't treat everything equally. Graph neural networks is again a very, very interesting one. Um, I think a lot of research has been going on in terms of network representation learning, and something that the MLN research team in Booking is also exploring on how we can leverage neural network based unsupervised learning on on graphs, like node to vec technology as well. So yeah, something more to come and might be worth sharing in the future conferences. But yeah, this is also something that we have been exploring and seems very promising. An analysis bit is again interesting. We also have developed an in-house tool for us that helps us visualize what the graphs look like. As I was mentioning, a normal typical user's graph could look something like on the left-hand side, with a few credit cards, with a few devices, with a particular email. However, a fraud trend could look something very different, and that's something, flowers of thousands of nodes connected with a single, either a single device or a single email. Right. So we have also built this, and it helps the fraud analysts and also the machine learning people to come up with new features and see what new patterns we can decipher in the world of fraud from the graphs itself. I'll briefly mention the next steps and challenges that we have before I close off my presentation and open the floor for questions. Some of the technical challenges that we have is how we can scale this technology not just to the world of payments but other use cases as well. Booking being not just focusing with payments to its customers but also has properties being registered on our platform, and fake properties can also be are also being registered, and we are trying to model even that problem in terms of graphs and see if there are common links which we can leverage and understand what the fraud scenario looks like there. Also in the worlds of accounts takeover, where guests and partners accounts are being taken over and important data is being leaked, and how we can model again accounts and devices and email addresses in forms of graph and stop accounts from being taken over. Another technical challenge that we have is how we can explore different type of graph databases, more managed and cloud native solutions. Right now, Genesis Graph works well for us, but it has its own challenges when it comes to maintenance and operational overhead. So we're also looking in terms of more cloud native solutions like AWS Neptune or Tiger Graph, and see how we can plug and play with different databases, keeping the rest of the business logic and framework as it is. Some of the business challenges again as that we have is once we expand to different use cases, how we can again leverage graphs to combine all of them together and view a whole kill chain from partners to guests to accounts and everything, and see how the fraud trend is evolving over the period of time and how the graphs can help us understand those trends better as well, so that in the industry of fraud, you always have to be one step ahead of the fraudster. So before they start learning new techniques to bypass your controls, how can we be more proactive and learn from the graphs itself? Yeah, I think that concludes my presentation, and I think we still have around 5 minutes left. So, would be very happy to take any questions. Feel free to use the chat that you have in the session, and yeah, I can help answer. Thank you. Do you have any questions? Yeah. I don't see anything popping up yet, but maybe someone is still typing. Yeah, also feel free to connect with us if you guys are interested in knowing more about booking or fraud in booking or how we are using graphs overall. And I think, yeah, you can find me on LinkedIn as well. What I can probably do is I can just drop my LinkedIn ID on the chat. So if anyone wants to even connect after the session, feel free to find me there. Okay, I guess there are no questions. If someone has something, just maybe feel free to connect with me on LinkedIn, and yeah, I can answer it there. Thank you so much, and yeah, have a great rest of the evening as well.